Okay, take it away, Claude.
Okay, thanks, Tom. So good evening. Welcome to the East Valley Astronomy Club virtual meeting. I'm Claude Haynes. I was president back in 2015. So I've resurrected one of the old meeting slides as a start. So I look forward to us having some fun tonight. And let's, if I can get my thing to move. So again, welcome. It's an image of the James Webb. I think we were all thankful, and it was a great Christmas present for it to successfully launch, and then over the last month, completely deploy. Considering all of the hundreds of things that could have gone wrong that didn't, that's pretty amazing. And it's just about, it's almost 90% of its way to L2, and its orbital point. And as Tom had mentioned earlier, toward the end of the year, 6 months from now or so, maybe summer, we'll start getting some imaging as they kind of get all of the instruments properly cooled and operating. So that's a great thing for us. Just would like to mention we have the officers and board, and since we are now starting a new year. I'm president. The vice presidential position is still open, and we are looking for volunteers. Tom has graciously helped us for the next few months to line up speakers, so we have a head start on that, but he doesn't want to continue in this kind of limbo position forever. And if you are interested in volunteering for the vice president position, give me an email, let me know. We are actively looking, and we would like to have somebody volunteer, and we hope that you will consider it and seriously think about it. Our secretary now is our former president, Gordon Rosner, and our treasurer is Alexandra Nachman, who has successfully weathered the transition with Brooks, with all of the accounts from Wells Fargo and Stifel and all of the minutia for a very difficult job, and we're looking forward to her taking that on and running with it. Our board members, David Kosho, John Kester, Bill Peters, Brooke Schofield, and Derek Youngson. Those are familiar names. Dave is joining the board after being the observatory manager and kind of having stepped away for personal reasons for a year or so, now back as a board member, so that's a good thing. So these are the officers and board members. If you have anything that you need, the contact us on the website has links, email links, or some of you have personal links, but let us know. We do want to hear from you. Your input is important to us, and if you need anything, let us know. This is a quote from Carl Sagan: "Not explaining science seems to me perverse, but when you're in love, you want to tell the world." This is a fairly romantic quote, but it is a reminder that we would like you to support the club and be in love with the club, to renew your EVAC membership. This is a method of supporting the work that we do, the program of our meetings, unfortunately by Zoom now, but hopefully at some point soon, I'm touching wood, we will be able to return to the live meetings. And in terms of our outreach activities and other things, this provides a way of supporting those, because there are expenses for the club. Even though we try to be as efficient as we can be in spending, there are things that we need support for, and we appreciate your donation to the club to support our activities. This evening we have a member presentation from Hanaan Abdulle, who is an ASU student. Some of you may remember her. I think she did a presentation a few months ago on her summer camp project on transitioning exoplanets, and we're glad that she is with us tonight. So I'm going to stop sharing my screen. And then if you would like to share yours, I think we're in business. And you're on mute.
All right. Hello. Just 1 second. Gotta share this one. Is it shared? I don't see it. Oh no. Oh, here it is. Perfect. Okay. Hello everyone. My name is Hanaan Abdulle. I also go by Hani, and today I'm going to talk to all of you about the opportunities in K through 12 astronomy camps. So to start us off, I'm Hanaan. I'm a freshman at ASU, and I'm currently studying astrophysics with hopes of working in museums to develop astronomy exhibits as well as camps, so informal learning for astronomy. I'm currently a program specialist at the Science Center, so that means that I do outreach events for schools and family nights, and then I also do planetarium shows and maintain the telescopes. And I'm also a Gilbert native. Um, and something that's really important to me is because as a kid, like many of you probably, I really liked astronomy, and it was really upsetting being a kid that liked astronomy because if someone likes bugs, at some point in biology class, we're going to learn about bugs. But throughout all of the science courses in elementary school and in middle school and even in high school, astronomy isn't given. So there's like a lack of astronomy in schools. And at the Science Center, we would have schools come in, and I'll do the planetarium show for them. And there will be kids that are fifth grade, sixth grade that have never even knew what a galaxy is or what a nebula is. And so the lack of astronomy education is frightening because afterwards every single child that came through the planetarium all of a sudden wants to be an astrophysicist. And although that's great, I wish there was opportunities for them to learn about astronomy in schools and also camps because as a kid, again, I really wanted to go to an astronomy camp because it sounds like the coolest thing ever. But the nearest astronomy camp was in Tucson, and I believe a lot of students have parents like mine, and I was not allowed to go to Tucson. So that was a problem where there's no camps around in the metropolitan area. And activities for astronomy can kind of be tricky, but doable, and yet there hasn't been many. So throughout my elementary, my middle school, even most of my high school, I really didn't have the opportunity to engage in astronomy outside of stargazing or reading science books. But then I was able to join the SCENE program as an intern my senior year of high school and did my exoplanet transit study and competed in the science fair and got third in division. But that is not ideal. What's ideal is for opportunities of science engagement in astronomy for students that are K through 12. And one way that we can do that is through engaging in camps. So last summer, I was the camp instructor for the first year of doing the Astrocamp. And although it is a NASA funded camp, NASA gave us certain activities that they recommended to use. And one of the activities, which is a good example of what not to do for a camp, is a Kepler's laws activity where I would explain to them Kepler's laws, and then I would hand them a worksheet and have them do the math of what Kepler's laws represents. I don't know about many of you here, but if I went to a summer camp and was given a piece of paper and a pencil, I would have left. So we decided not to do that activity. And the reason why is because in informal education, the strain isn't on meeting core curriculum or having a test at the end of the camp. The root of it is to create and cultivate a culture of science literacy or science engagement, and for these students to continue on and in the following school year think of science as not something that's drudging and a task and is hard, but something that can be exciting and something that they want to do. So the example that I have here is one of my students where we developed an activity about galaxies. So we, in the beginning of the camp, I asked them all For those of you that like astronomy, what is something that you've always wanted to learn more about? Every single one of them said, what in the world is a galaxy? Perfect, we started there. So we talked about galaxies and how they come in different shapes, and they looked, there's certain classifications of galaxies. And then the children were able to use these beads to create their own galaxies. So the activity is that they learn something, and they also get to use their hands and use their minds to create something from what they've learned. And so creating and engaging in an innovative activity is really important for these informal engagements in astronomy education. And the perfect thing about Arizona is that we have so many resources. ASU, the School of Earth and Space Exploration, is perfect as a student in that school. I really love it, and I believe that the possibilities for field trips for these camps would be incredible, since the amount of labs and the minerals that are there at the school would be great for the kids to learn about. And then also the East Valley Astronomy Club. All of you, all of the members here, most likely have had experience with a telescope, with amateur astronomy. Maybe some of you have also even hosted or been to a star party. And so these are all things that through all the time that you've accumulated of engaging in astronomy, that to mentor students and kind of engage them in the fact that astronomy doesn't have to be a purely professional pursuit. It can be something that you enjoy as a hobby as well. And then the Science Center, as I've mentioned before, the planetarium is great because kids get to see the night sky as it can be and learn about practically anything that they want to know more about. So where do you all come in? So this summer, we are in fact hosting another astronomy camp. The astronomy camp for last summer was geared towards younger students. So we had third through fourth graders, fifth through sixth graders, and I believe we had some second graders. But this summer, we are a little bit more ambitious, and we want to gear it towards more middle school and high school. And so that will require a little bit more developed activities. Like, for example, I'm currently developing an exoplanet activity where using a photoresistor and Arduino and a box with a light source and a planet that's on a motor, where children can change the speed of the planet, also changing the distance the planet is from the host star. And looking at the light curve fitting, they can learn about how we study exoplanets out in the night sky without having to learn about the necessary telescopes or the coding required to do that in an actual setting. So they get to learn about the science behind it without having to deal with the logistics of it. And then also, if anyone is interested in participating in assisting the camp through helping us with our family night, we are also hosting a star party for campers and their families to for the campers to kind of show their families what they've learned about the night sky, and also for them to engage in stargazing as a activity for all of them to learn more about. And then also my email, if anyone is interested in any of this, you may email me and let me know, so that as we begin to organize more and more for the camp this summer, I can keep that in mind. And thank you.
Thank you, Hani. If anyone has questions, please put them in the Q&A. If you're a panelist, we don't have access to the Q&A, but we can just ask out loud. So, Hani, I'll start with a question. When you say the camp, will there be several sessions during the summer, or is just one or two?
So the way that we do the camps is that each week is a theme. So in June and July, they're mirrored. So we'd have a week of Astrocamp in June and then a week of Astrocamp in July.
What? I'm sorry, one in June and one in July, you're saying?
Mm-hmm.
And is it at, where is it located?
It's at the Science Center.
Okay, and then they come every day in the morning, or, and if weather permitting, maybe you can do some observing? in the evening?
So the goal right now is for the high school age students that it would be a Monday through Friday, and there would be an observation night, hopefully on a Tuesday or a Wednesday, so that because the high school students would actually be doing an exoplanet study. Is the goal.
Okay, let's see. So there's a couple questions. I think Brooks just asked where and when. We just answered that. That was June and July. June and July at the AZ Science Center. And then another comment was, does your organization have a website?
Yes, it's the Arizona Science Center. You'll just have to look up the site.
Okay, and is there's subcategory when you go to that page?
There will be camps. So you'll look at camps.
Okay. And let's see, yeah, so we'll have to put that in the newsletter if you wouldn't mind writing up a little paragraph.
Yeah, for sure.
And then you can come back from time to time and remind us that you still need help.
It will do that.
Okay. Yeah, a lot of kudos. I think that's it. Tony George, I might have had a question. I don't see the rest of it. Okay. All right. Well, thank you very much. Yeah, we'll try and coordinate with you and get you some help. Or yeah, maybe you can tell us what exact areas you need help in. I know you said planning, but
So for volunteers, it would mainly be the building of the exoplanet activities. So it would require some, not like incredible amounts of knowledge about like Arduinos, but kind of like a baseline understanding of how to create the circuit for the photoresistor. And then we have the benefit of the Science Center is that we have a workshop. So we have 3D printers, and we have like a wood shop, welders. So it's like kind of like more engineering focused.
okay. So you have the plans for this. You just need some assistance in helping people put it together.
Yeah.
Okay. Let's see. Do people need to know how to program Arduinos, or will they be shown?
It'll be shown because I'm
Okay.
still changing the code for that one.
Okay. Yeah, you use one of the environments, right, to program it. Okay. Let's see. Any more? I think that was it. Okay, great. Thank you very much. Okay, so on to our featured speaker. I'll introduce Steve Desch. He's a professor of astrophysics at ASU in the School of Earth and Space Exploration. Studies formation and evolution of planets, the origins of the solar system, exoplanets, and meteorites. He has written about Oumuamua, I hope I said that right, in the popular press, and is thrilled to have contributed to our scientific understanding of this unique object. Steve also has an asteroid named after him, right?
Oh, yeah, I do.
Okay, that's cool. Let's
996.
see. So yeah, I'll stop talking and hand it over to Steve.
Super, thanks. Thank you, really. And by the way, I can't get this to bigify and go into presentation mode without crashing PowerPoint, so we're just going to do it this way. But I'm looking forward to coming in person, as are we all. I realized I frequently give talks to the East Valley Astronomy Club. I gave one 5 years ago yesterday, and I'm looking forward to it again. I'm always happy to meet all the people. So thanks for having me. Yeah, so I want to talk about Oumuamua, which is an object that came through our solar system. Well, it's really still in the process of doing it, but it came really close to Earth about 5 years ago. And it is the first object discovered to have come from outside of our solar system to come through it. So it was discovered in October 2017 and from the Pan-STARRS telescopes in Haleakala. And this is an image from other telescopes in the Canary Islands from around that time. There it is, a little dot. And it was like a comet in some ways, and yet it was not like a comet in other ways. And so it's been a little bit of a mystery as to what this object actually is. So some of the mysteries about it is, you know, this Pan-STARRS array of telescopes in Haleakala was only operational a few years when it found this object. So it leaves us with the impression that these objects are found pretty frequently, and that would mean there must be 10 to the 15 such objects for every star in the galaxy, which seemed like a high number. I'll tell you why that seemed high. It also entered the solar system at a velocity which was a little hard to understand and pushed away from the sun a little bit faster than you would expect for if it were a comet. It had a really weird shape. It was either very skinny like a cigar or more likely like flat like a pancake, but very extreme, like no other object we'd seen. And there was no dust, no CO, no gas coming off of this. It was just this little dot. So none of this made sense. And so the question is, what is it? And it's become very popular to talk about in the public sphere. And it's been suggested that it's a spaceship of all things. And so I want to give you a natural explanation for this. I'm pretty convinced that it is a piece of ice. It's a piece of ice like we've never seen in this context before, though. It does match, though, everything that you would expect a piece of ice to do if it were a piece of frozen nitrogen ice, like we see covering the surface of Pluto. So if you were to knock a piece of Pluto's crust and make it go by the sun, it would look exactly like this thing. That's what I want to show you. And I want to convince you that the sun, the solar system, probably ejected around 10 to the 15 fragments like this from in the early days of its evolution. And so I think the natural explanation for Oumuamua is that it's a piece of an exo-Pluto and a fragment of a Pluto-like exoplanet that came by Earth, and that would make it the closest any exoplanet has come to us. But let me get into it then and talk about it. Yeah, so unfortunately the animation won't work, but it came in on a kind of strange orbit outside the solar system, moving pretty fast, approaching at really 26 kilometers per second. And keep in mind, the Earth is orbiting the sun at 30 kilometers a second. Came in from this direction. It actually went by the sun. Can I actually make this work? Oh, look at that, it's working. So it came by the sun, perihelion, on September, and then it flew by Earth in October, and it approached within 0.16 Earth sun distances. It was observed by telescopes at this time, and including the Spitzer Space Telescope through November. But after that, it was just too far away and too small and too faint to observe. And I'll play it one more time. But it is now traveling outside the orbit of Neptune, I believe, and it is on its way out of the solar system to return back to the galaxy. From a different perspective, you could see the stars that it's in front of over time, and there's a huge parallax effect here. As it gets closer to the solar system, it started to make these excursions, and at its closest approach it was here, and then so we saw it after it reached perihelion. That's kind of important for the story here. And then it was observed by Spitzer, and now it's going off in this direction. The direction it came in from is near the constellation of Lyra, star Vega. And that is actually a special place in the sky called the solar apex. And that's a clue to where this thing came from. If you look at the proper motions of stars, you see that over centuries, they are kind of moving through our sky. The closer ones are moving faster. And if you could watch for long enough, you'd see that there's a general trend for stars to be moving away from this point, the solar apex near the star Vega. And it's like you're driving the solar system through a blizzard, and the stars, like snowflakes, are going by us. And this has to do with the sun's motion through the galaxy. So you can get a view of things. What we see about the velocities of stars near us is that they're all kind of random relative to the sun, relative to the sun, they on average have sort of average velocities, and we call that average velocity the local standard of rest velocity. And so all the stars are kind of going around the galaxy. They tend to have a sort of average, but they also have this random velocity as well. And so some of the stars are going this way, some are going around the galaxy faster than the sun, some are going a little bit less fast. And the sun has its own average, it's random velocity with respect to this average. And it is going in this direction, the same as its motion around the galaxy, at an extra 18 kilometers per second or so. And Oumuamua, this object that came from outside the solar system, approached us at about 26 kilometers per second, but most of that was the sun's motion this way. And so that means that it was actually moving with respect to this average velocity, this local standard of rest, at about 9 kilometers per second or something like that, a pretty small velocity. And hopefully this also gives a sense of what's going on. The sun and all the stars in our vicinity are orbiting the galaxy. It takes about 250 million years for them to go all the way around. And this swarm of stars is moving in this general direction. The sun is moving this way a little bit faster than the average around the galaxy. And so that's its motion around the galaxies this way. And then all these other stars are swarming around it. All right, so when we say that Oumuamua moved kind of slow, what we mean is that with respect to the average velocity, it was only moving 9 kilometers per second, whereas most of these other stars are moving 20, 30 kilometers per second relative to the local standard of rest. So that was one weird thing about it. Another weird thing is the shape. And the shape is not something we could observe directly. Nobody ever got a picture of Oumuamua that looks like this. These are artist rendition. But what we could do is look at the amount of light that was reflected off of it over time. So it's just a little dot in the sky, but that dot would get brighter to 22nd magnitude to be precise, and it would get dimmer down to 25th magnitude and brighter and dimmer again with a period of about 8 hours. And over this time, it would get very dim and bright. And you know, it's hard to imagine that it would have a dark side and a light side that was so extreme that you could get this huge variations, you know, factor of 10 variations in the amount of light that it's reflecting. And anyway, it's really hard to explain the shape any other way, but it's really easy to explain the shape if you model it as either a cigar or a pancake that is flipping, rotating through space. Because with a cigar or a pancake, there's going to be a time where you're looking at it along the long axis or edge on, and then it will reflect a lot less sunlight. So models have shown that either of these models could explain these light curves. And in fact, the pancake shape like this is more likely and fits the data a little better. So we infer that it was shaped kind of like a pancake with axis ratios about 6 to 6 to 1. So it's only 1/6 the thickness compared to the width. And it also reflected red light a little bit better than other lights. So it would look reddish. That part is right. Who knows if it has a crater or whatever. But that's an extreme shape. There's no other object in the solar system that is so extremely shaped. Usually chunks of asteroids, the axis ratio might be 2 to 1 or 3 to 1, not 6 to 1. All right, some other weird things. It was moving very fast, of course, as it went by the sun, and it approached the sun at only a distance of 0.25 AU. Astronomical unit is the Earth-Sun distance. Mercury is at 0.4 AU. So this object got closer to the sun than Mercury, and it was moving at 88 kilometers per second. And as it left the sun's gravity was pulling it back and slowing it down, and it was decelerating, but not quite at the same rate that you would expect just purely from gravity. So there was some extra force on the object that was preventing it from slowing down quite as much. And it's a small effect. It's about 1 part in 1,000. And you know, it was slowing down, but just 1 part in 1,000 less than it would be if purely gravity was acting on it. And we know that comets do this. Comets also, as they go by the sun, they decelerate, but not quite as much. It's as if they're getting a push away from the sun. And that's exactly what's happening, because as this image from Rosetta shows of comet 67P, the sunlit side is being heated and ices are sublimating, gases are pushing off from the surface, and it's really just like a little rocket. And so the gas is pushing off from this side, and you can even see this jet here. They're like little rockets, and they give it a push away from the sun, and the sunlight is what's heating up those ices. And so the amount of sunlight hitting them is varying as 1 over distance squared from the sun, and kind of like same gravity as gravity. Gravity goes as 1 over distance squared. So this effect is always some fraction of the force of gravity. For comets, it's generally 0.01%, and for this object it was 0.1%. So it's very much like a comet, but we had never seen a comet with such a big push like this. And in fact, you could show from calculations that water ice would never give you this sort of push. So that's been a mystery. That was a mystery as well. So a lot of these mysteries were compiled by Harvard astronomer Avi Loeb and written up as papers. And some of the mysteries are just how many of these objects there must be. Again, we saw one, seemed pretty soon after these telescopes became operational, and the odds of that imply that there must be quite a lot, something like 10 to the 14, 15, even 16, somewhere in that range, objects for every star. Now, interstellar objects have been expected for a long time, because we know that our solar system has an Oort cloud of comets that are just barely bound to the sun, and models show that for every comet that is just barely bound to the sun, probably got there by Jupiter's gravity acting on it, there must be 4 times as many comets that escape the sun altogether. And based on how many comets we see, how many we infer to be in the Oort cloud, we kind of expected our solar system to eject 10 to the 12 comets. So it's been expected for a long time that there should be such objects, but these numbers that Oumuamua implied are orders of magnitude more than the number of comets we expected. As I said, the velocity of Oumuamua with respect to the average velocity of stars was only 9 kilometers per second, maybe only 6, somewhere in that range, whereas most stars generally move at 20 to 30 kilometers per second relative to the local standard of rest. So if this were a natural object ejected from a star, the thinking was that it should also have the velocity of its parent star and should be moving faster with respect to the local standard of rest, and yet it didn't. It was very elongated, and it had this non-gravitational acceleration. I talked about that. And then also the Spitzer Space Telescope observed it and looked for infrared emission, and it would have seen carbon monoxide or carbon dioxide or water if those species were present in sublimating from the object. Certainly if the sublimation of those ices is what's giving it the push that we saw, then Spitzer would have seen them, and it didn't. And not only Spitzer, but even optical observations didn't see any dust, and that was really a tight constraint. Like there really couldn't have been a lot of dust, whereas comets have dust. So there you have it. There's a bunch of mysteries about this object, and this all came into the scientific literature in 2017 and 18. So proposed explanations. There were a lot of papers that tried to explain one feature or another of Oumuamua. And first thing being, how do you get such an extreme ratio? And at first, people didn't think it was comet-like or made of ice. And so there were a lot of explanations based on the idea that maybe it was an asteroid. And if it's an asteroid, it's really hard to get it to be such an extreme shape. And there were ideas that maybe an asteroid on its way out of its solar system went by its star and was tidally stretched and disrupted. Maybe that's it. Another explanation, though, is that maybe it is made of ice or somehow is eroded, maybe by dust in the interstellar medium. And it is a neat feature that if you take something that isn't quite spherical and you erode it over time, if you remove the same thickness from every side of it, then eventually it's going to get more and more elongated. So this has an axis ratio of something like 2 or 3 to 1, but by the time you erode it significantly, then it's extreme, like the 6 to 1 ratio we see for Oumuamua. So the extreme shape kind of implies that it suffered a lot of erosion. This thing has been in interstellar medium. Maybe there was something that eroded it. So that made sense, but what is the composition? What eroded it? All these things were not known. I'm going to skip this slide. And then there's the non-gravitational acceleration, that push that it got as it moved away from the sun. And on the one hand, if it were ice, it couldn't be water ice, it couldn't be carbon monoxide, it couldn't be carbon dioxide. And there were a lot of thinking that it just couldn't be any sort of ice that we were familiar with. This paper purported that maybe it was made of frozen hydrogen gas. And that's possible. If you can get below 3 degrees above absolute zero, hydrogen gas will freeze, but we've never seen hydrogen ice in any other context, and it doesn't seem likely. Based on the idea that the push was going as 1 over r squared, but could not be ice, supposedly, Loeb and Bialy proposed that maybe it was radiation pressure that was pushing the object. And this is the principle behind something we call a solar sail. Maybe you're familiar with this, that you could have a very thin sheet of mylar, and the radiation from the sun has some momentum and can push on it. And that would give you a push that would also go as 1 over r squared. And so they really got stuck on this idea and started proposing that it's a solar sail. Obviously, we didn't build it, so it had to be of alien construction. And in fact, Loeb has written a book that he'd like you to buy that is called Interstellar, and it claims that this is the first object of alien manufacture that we've ever seen. Well, okay. What I'm trying to convince you, though, is that this is a very natural explanation, and it is a unique object, but it's made of ice, basically. So getting back to the shape, this work by Meschenko in 2019, I carefully showed that it was probably a pancake shape. And I just want to point out that before that work, actually it only took a few months, but the first thing that people thought of was that it was cigar shaped. And if you see a cigar shaped object coming from outside the solar system, you're going to immediately think of Arthur C. Clarke's Rendezvous with Rama. And so it was very natural to think about a spaceship. It's kind of a pity that they didn't realize right away that a pancake shape worked better than a cigar. But we're pretty sure that it had 6 to 6 to 1 axis ratios. And these would be the sizes if the object was reflecting 10% of the sunlight that hits it. So its albedo is what we call the percentage of sunlight that's being reflected. So if its albedo was 0.1, it's reflecting 10% of the sunlight. And that would be a very typical number for comets or asteroids in our solar system. And based on how bright it is and how much light we're seeing, and based on that reflectivity, it would demand these ratios of, or these sizes of its axes. And that would be the diameters there. But one of the things that my colleague and I, Alan Jackson, is a postdoc in our department at the School of Earth and Space Exploration, and he and I worked on this together. We realized that a lot of people are just assuming that it would have this albedo of 0.1. And that would be good for an asteroid, but we're talking about an object that got a lot of push away from the sun, probably not an asteroid, probably an ice. And ices are pretty reflective. So we started to imagine what would happen if it were reflecting a greater fraction of the sunlight. And what that would mean is if it were reflecting a greater amount of sunlight per area, then it didn't have to be as big. And if it's not as big, then it's certainly not going to be as massive. And the amount of push you get from sublimating ices is going to look larger. And in fact, you can just tabulate this, that the cross-sectional area is going to be proportional to 1 over the albedo. So the diameter is proportional to 1 over the square root of the albedo. The sunlight that's actually reflected, or I'm sorry, absorbed, that's what's going to heat up the ice, is the amount that's absorbed. That's proportional to 1 minus P. But you can figure out the force and then divide the force by the mass. The mass is going to go as the radius cubed. And anyway, you get that the acceleration should scale as this quantity. So it's certainly possible to have the object be low albedo, but we realized if you had a high albedo, you could actually get a bigger acceleration. And that's in this term here. All right, so at that point, we decided this is worth calculating. And so Alan compiled information for all the possible ices that exist that we thought could be reasonable things to look at. And we were sort of motivated by some other work people did, the Seligman and Lofman paper. They had a similar table where they were looking at hydrogen ice, but you know, we also looked at the ices they did. We also rederived this equation for the acceleration that you get when you sublimate ices off of an icy body due to sunlight. And that's the equation. I'll just leave that up there. So we compiled all this information, we derived the equations, we did some math, and we came up with this graph. This is a graph of the acceleration that you get, and it's scaled to the acceleration you need. This is the part of the acceleration that is not due to gravity, the non-gravitational acceleration, that little extra push it's getting away from the sun. So that acceleration that you get from sublimating ices that we predict is the thing we're trying to model here, and we're scaling it to what you see Oumuamua had. And so we want it to be 1, basically. And that's a function of the albedo, the surface reflectivity here, and of course the composition. So for different compositions of ice, like water ice, we can ask how much of a push do you get if you leave the albedo be a free parameter. So water is never going to give you enough of a push. It's always going to give you something like a few percent of the push that you need. Sublimating water ice isn't going to work. Sublimating hydrogen ice works, but also it works way too well. You just cannot keep hydrogen ice from sublimating. As soon as it gets to sunlight, it gives it a huge push. And so that doesn't really work. And for a lot of reasons, we can rule out all of these other species. But one thing that works really well is frozen nitrogen, N2. So the same stuff you're breathing right now, if we were to freeze it, make a chunk of it, that ice, we would get the push you need. And there's 2 solutions for the albedo, actually, a low and a high albedo. But the high albedo solution, you would need an albedo of about 0.63. And if that were the albedo of the surface, nitrogen ice would give you the exact right push. And the neat thing about this is if you look at the surface of Pluto, which is 90-something% frozen N2, you see that its albedo is exactly this. So we thought this was a great aha moment, that if you have a chunk of Pluto's surface, it would have the albedo that you need and the composition you need, that if you put it near the sun, it's going to sublimate and give you exactly the push that we see. And Triton is another object with nitrogen ice on its surface, but not pure nitrogen ice. These albedos are ruled out because Spitzer would have seen the infrared radiation if it were very big, and low albedos like this would require it to be too big. But this just works perfectly. And moreover, the surface of Pluto is exactly as red as Oumuamua looks like. So we thought we were onto something here. We calculated how much mass you lose, though, because remember, if you're sublimating nitrogen ice, then you're losing that nitrogen ice, and the push that we're getting from the sublimation is eventually going to use up all the nitrogen ice. So we could calculate the mass of the object as it went by the sun. So right here, this is a graph of the distance from the sun over time. Perihelion is here. 0 is when it was discovered arbitrarily. So it was discovered a little past perihelion. So it goes by the sun. We calculated its orbit. This is the surface temperature. This just amazes me that it never gets above 45 to 50 Kelvin. And you would think that an object closer to the sun than Mercury would get super hot, but it's losing nitrogen ice so fast, it's sublimating so fast that it actually is experiencing a considerable amount of evaporative cooling, which all of you in Arizona know this. When you step out of a pool and you're wet and the water's evaporating, even though it's 110 out, you start to shiver. So same idea here. This object was losing ice so quickly that it actually stayed at 45 Kelvin. Nevertheless, it was losing mass like crazy. So it lost about 95% of its mass by the time we observed it at time 0 here. So it went by the sun and it lost so much of its mass. And the loss of all that material is going to exaggerate any non-spherical shape it has. And so we realized if it came into the solar system with an axis ratio of 2.4 to 1, which is actually something we see fragments, pieces of asteroids and things like that. They often have that sort of axis ratio. By the time we'd observed it, it would have been that 6 to 1 that we see. So it just all hangs together. And the non-gravitational acceleration, by the way, this is what we predict. And it's right in line with what was observed. And so it's just perfect. So, okay, I'm going to leave it at that. So all of the features of Oumuamua are, everything we observed about it is explained. If it is a chunk of nitrogen ice, that is very similar to the composition of Pluto's surface. And that would be exactly as red as we observe Pluto to be. And also Pluto's surface ices, they have a tiny bit of CO, carbon monoxide, some methane, but at these levels, if Oumuamua also had similar levels, we would not have detected it with Spitzer. And yeah, Pluto has kilometers thick surface of N2 ice. So on the one hand, yes, this explains it perfectly, but the question then becomes like, how do you get so many chunks of nitrogen ice ejected from basically every solar system in the galaxy? Because remember, there has to be 10 to the 15 objects like this per star in the galaxy. And we can only begin to answer that question by thinking about what happened in our own solar system and asking whether at least our own solar system would have ejected similar numbers. So we have to think about solar system history to see whether a chunk of Pluto's surface is a likely thing. And I should point out that nitrogen ice, we see it on Pluto, we see it on Triton, we might see it on a few other objects, but we generally don't see N2 molecular nitrogen. We certainly don't see a lot of it on comets. Only 1% or 2% of the total nitrogen atoms in a comet are actually in the form of N2. And we know this from observations of like 67P, which was imaged up close by the Rosetta mission. In fact, they found where all the nitrogen is. It's been a mystery for decades. Where is all the nitrogen? Because we don't see it in N2 gas, and we see a little bit of ammonia, but not enough to explain where all the nitrogen comes from that we think our solar system was born with. But they discovered that 67P has half of its nitrogen is in ammonium salts on the surface. So that's pretty cool. And so you would not get nitrogen ice from comets. You wouldn't get it generally, but you do get it on Pluto's. And the reason is probably because inside a Pluto-sized planet, you have subsurface oceans. And in a hydrothermal system or in an aqueous environment, it's actually pretty easy to convert that ammonium salts and the ammonia into N2 gas. And N2 gas will make it to the surface. And again, we see Triton's surface is covered with nitrogen ice, and Pluto's especially. And it's very hard to observe nitrogen ice spectrally. It's actually very difficult to look at ice and tell that there's N2 ice in there, especially since it's never going to be it's not usually a major component of ices, but we think there's hints that some of these larger Kuiper belt objects besides Pluto, and Triton might also have nitrogen ice, but it's hard to tell. It's just inconclusive, but Pluto certainly does. And so we can ask, how did Pluto get it? And it's probably a universal process if Pluto has it. All right, so models of Pluto's interior have shown that it almost certainly heated up enough when it was born that you melted the ice and the water ice, and you allowed rock to settle to the center by its own gravity, and water ice would form a mantle around this. So we're pretty sure that Pluto and other large Kuiper belt objects like I just showed you, and I'm going to make reference to Pluto, that's a thing we're all familiar with, and this one, Gong Gong, which is just convenient because it has about half the radius as Pluto. But these objects in this size range almost certainly divided themselves into a rocky core and a water ice mantle. And in fact, the water ice mantle is hot enough that a lot of it is liquid, and probably it's still liquid on Pluto. Pluto probably has quite a lot of water beneath the surface. But it's in this environment that you can turn nitrogen into forms like N2, and N2 wants to be a gas that will bubble up, and it won't dissolve in the water. It wants to bubble up and erupt onto the surface. And so it certainly did that on Pluto. It probably has done this on other Kuiper belt objects. And once it's on the surface, it freezes. And this is probably why Pluto has so much N2 ice. It's very easy to lose N2 ice once it's on the surface. So it's hard to tell how much was there in the past. But if you just count up how much nitrogen these objects have, and you think about their interiors, there was probably enough nitrogen in a typical solar system composition that Pluto could have had an N2 ice layer up to 35 kilometers thick. And it certainly has one that's a few kilometers thick today. And Gong Gongs could have N2 ice layers that are up to 18 kilometers thick. And these subsurface oceans don't take long to form according to models, probably only a few tens of millions of years. And so I think it's a reasonable assumption that Pluto size and Gong Gong size objects probably had these thick, tens of kilometers thick nitrogen ice surfaces. And there was probably quite a lot of nitrogen ice to be ejected from solar systems, but the missing link here is, how do you get it off the surface of a planet and eject it into interstellar space? Okay, so to get to that question, we have to think about what was going on in the solar system early on. And maybe some of you have heard about the Nice model that was developed at the Nice Observatory in France around 2005. And this has been, a revolutionary model, although it's already 15 plus years old now. But at the time, I said this is to solar system evolution what plate tectonics is to geology. It was this unifying concept. Until it came around, I don't think we appreciated how much the planets moved around. But we do now understand that probably the giant planets, Jupiter, Saturn, Neptune, Uranus, probably formed in that order, and probably exists between about 5 AU, which is about where Jupiter is today, and 15 AU, which is today, that's between Saturn and Uranus. But the solar system probably formed the planets in this configuration. And there was probably this primordial belt of objects, the primordial Kuiper belt, that existed between about 15 and 30 AU, and had 35 Earth masses of objects. And of course, today, the Kuiper belt is something that we think of as existing beyond Pluto only, and it has not even a tenth of an Earth mass of material. But back at the birth of the solar system, there was probably quite a lot of material. And maybe this was Pluto's, maybe this was comets. For the purpose of the Nice model, you kind of need, a lot of it could be small objects, and you need some Earth masses to be in Pluto-sized objects to make this model work. So what happened, why isn't it the same today as it was when it was born? What happened is that the gravity of these planets perturbed these guys' orbits. They tended to drift into this region. We see this process exists today. There's Kuiper belt objects that make it between Saturn and Uranus. They're called centaurs. And anytime it went by a planet, a Kuiper Belt object or some other massive object could get a gravity assist. It could be ejected further out. It could be ejected closer in, just the way our spacecraft get gravity boosts. But when that happens, it also has an effect, an equal and opposite force on the planet. Usually we don't think about how much of a push our Voyager spacecraft put on Saturn when it went by Saturn, because Voyager is so much smaller than Saturn. But when you have this process repeated trillions of times and they add up to 35 Earth masses of objects, those pushes and pulls add up and they can change the orbits of the giant planets. So as these objects interacted with the planets migrated to different places. And the net effect is that Saturn, Uranus, Neptune moved out and Jupiter moved in. And the way to remember that is that these guys will stick around the solar system, and on average, they fly by Neptune and they give it a push in, or then it comes around again and gives it a push out. Those average out to 0. The only way you leave an effect, a mark on the planets, is when that object is ejected from the solar system. And most of them are ejected from the solar system when they fly by Jupiter. So the last time Jupiter sees an object, it gave it a kick out of the solar system, and that tends to leave it with an inward migration. The last time these planets saw an object is when they kicked it into Jupiter, and that means that they got a net outward motion. So anyway, Jupiter moved in, the other planets moved out. At the beginning, Jupiter and Saturn were not orbiting at the same speeds they are today. Right now, Jupiter goes around the sun 2.5 times for every one Saturn orbit. But at the beginning of the solar system, Jupiter went around about 1.9 times for every Saturn orbit. And as you can imagine, there must have been an in-between time where Jupiter went around exactly twice per Saturn orbit. And it's that exact resonance that led to chaos in the solar system. Once Jupiter and Saturn went through that stage, Jupiter made Saturn's orbit very eccentric, and then it started interacting with Uranus and Neptune, and it changed their orbits. And computer models show that within 10 to 20 million years, 4 billion years ago, there was a stage where the orbits were just completely chaotic. Jupiter moved in, Uranus and Neptune probably interacted and switched places. There might have been another planet, maybe planet 9, if it exists. It was ejected from the solar system at this time. Anyway, it depleted the Kuiper Belt and it ejected a lot of material, and velocities were crazy, and it probably lost 80% of the comets and Kuiper Belt objects from the solar system altogether, and close to 20% were put into the Oort cloud. Only a fraction, 1 out of 1,000, actually survived and exist in what we call the Kuiper Belt today. A lot of these are swept up with resonances like Pluto is with Neptune. And today there's about 1/10 of an Earth mass, but there used to be 35 Earth masses of objects. What blew my mind when I started reading about this and researching this a few years ago is that there probably were 2,000 objects like Pluto in the solar system at this time, and 6,000 objects like that smaller Gangan. And now we just have Pluto, Eris, Triton, just a handful of objects, but there were thousands of them. And during this stage, this dynamic instability, the velocities of all these objects went crazy, and there were a lot of opportunities for collisions between them. So today it looks pretty quiet and quiescent, but there was a process that took about 10 or 20 million years to play out, probably happened 50 million years or so after the solar system got started, 4.5 billion years ago. And during that stage, despite the quiet appearance today, during that stage, it was quite chaotic and there were a lot of collisions. All right, and as I said, about 20% of all ejected things end up in the Oort cloud, 80% get out of the solar system altogether. All right, so yeah, during this stage, during the time there were all these collisions, each Pluto was probably pummeled by about a Vesta's worth of mass. And this would have sandblasted it and ejected quite a lot of material. And all in all, we think that there were fractions of an Earth mass of fragments ejected from the solar system. And these fragments would have been, some of them would have been water ice, but a lot of them would have been nitrogen ice. And so in this work, we calculated how much material was ejected. And it's incredible, but something like 10 to the 14 ice fragments were ejected from the solar system, and most of those would have been nitrogen ice. So, and of course, this nitrogen ice would have been eroded somewhat in the interstellar medium. And this is a clue if we think we understand the shapes of these fragments. The typical access ratio probably should have been 1.7 to 1, but after suffering irradiation by cosmic rays in the interstellar medium between being launched from its solar system and reaching ours, it would have been flattened a little bit to 2.1 to 1 access ratio. But anyway, yeah, most of that material would survive passage to the interstellar medium for billions of years and could enter our solar system today. So with that framework, let's just get back to these mysteries. This is that same list I showed you before, and ask whether these things seem so weird in hindsight. So first, like this one, could there have been 10 to the 14, 10 to the 15 objects per star? That seems like a lot. We only probably ejected 10 to the 12 comets. And that's true. The number of comets that were directly ejected was probably not that large, but we didn't only eject comets, we ejected these fragments. Every time a comet would hit a Kuiper Belt object like Pluto, it would eject way more number of fragments than that one comet. And so this explains exactly why you have exactly how many objects you do. When we think about a few percent of an Earth mass was ejected in the form of N2 ice fragments. And this is consistent with the statistics. If other solar systems ejected as efficiently as ours did, then as we think ours did, then that would explain the numbers. So it's really not that mysterious. About that velocity, the local standard of rest velocity, stars move with respect to it at 20 to 30 kilometers per second, but this object only at 9 kilometers a second. Does that make sense? And in fact, it makes perfect sense when you realize that, yes, whereas most stars are moving pretty fast with respect to the local average, young stars do not. If you were to just focus in on the young stars, ones that are less than 1 or 2 billion years old, they actually move more slowly. And in fact, the clouds, the molecular clouds they're born from, move pretty slowly. And it's actually understood that stars are born with pretty small velocities. And it's only after they've been around the galaxy a few times that they have these scatterings off of each other and scatterings off of molecular clouds, and they pick up these bigger random velocities. But if you're looking at an object that was ejected from a young solar system, then it actually should have a small velocity. That's perfectly normal. And we're talking about ejection during a dynamical stage that in our solar system happened way earlier than when it was 2 billion years old. So the material ejected from our solar system would have had these low velocities, and probably is true of others. Yeah, and that's what I just said. Now, how about that shape? The shape actually works out really well. That most of the flattening occurred when it lost 95% of its mass in our solar system. If we had seen it before it reached perihelion, it wouldn't have been so flat, and we wouldn't have thought it so unusual, but it's only because it was so small and so eroded by the time we saw it that it was such an extreme case. So it's actually understandable we don't see that. But we can actually use this shape to figure out some other things, like how long was it in the interstellar medium. This part's a little bit speculative because we don't really know how what its shape was when it left its solar system, but it is reasonable to think that it probably suffered a little bit of flattening before it got to our solar system. Most things aren't quite that flat. So it's consistent with being in the interstellar medium for about 500 million years. And it's a really interesting number to think about, because if the sun were moving this way around the galaxy and this object was coming in from this direction and it had been traveling for 500 million years, then that means that it would have come from the Perseus arm, the next spiral arm ahead of us in the galaxy. It would have taken about that length of time to reach us. So there's no way to prove this, but it's very consistent with the idea that it came from a spiral arm, the next one over. And that's really important because stars are born in spiral arms. And so a young solar system is most likely to be seen in a spiral arm. So that's that. The non-gravitational acceleration is actually, that was the point, N2 ice with the albedo of N2 ice exactly explains the non-gravitational acceleration. And the Spitzer observations tell us the same thing, that there couldn't have been a lot of CO or CO2 or dust, but guess what? Ice on Pluto doesn't, and ice from the surface of a Pluto-like exoplanet probably wouldn't either. So yeah, that's what I just said. Okay, so one of the other questions that comes up, one of the predictions of this model is that if you had objects like this ejected from the solar system, then some of these objects should have existed, should have been put into our Oort cloud and should come back as comets. And so it's actually a prediction of the model, and it's a test of the model. Are there any comets that are not water ice, that are like Oumuamua? And it turns out there is one. And one of the hundreds of comets that have been observed was this one called C 2016 R2. And it was already suggested that it is a piece of a differentiated Kuiper belt object like the surface of Pluto, because there was no water detected, no sulfur species detected. And those are some of the most common things in normal comets. There was very little dust detected. The most abundant species were carbon monoxide and N2, and N2 is never seen on any other comets. And so about 1 in 1,000 comets is what we predict looks like this, and that's kind of consistent with the numbers. Well, be that as it may, we are pretty confident that all of the features of Oumuamua, in terms of the things we detected about it, they're consistent with it being nitrogen ice that is compositionally just like the nitrogen ice that we see on the surface of our Pluto. And if other solar systems had Pluto-like exoplanets, if they ejected fragments of N2 ice at the same rates we think our solar system did, then the numbers, the statistics of these objects is also explained as well. And so that's our conclusion, that this is a very natural explanation. It is a chunk of nitrogen ice from an exo-Pluto, and other solar systems probably evolved very similar to ours. And Oumuamua was a piece of an icy exoplanet that passed by Earth. That's the end of my talk. Thank you. And to look at the and see how those.
Yeah, thanks, Steve. That's really interesting. Nice recap of the family history of our planets, how they got to be where they were today, you know?
Yeah.
Start off teenagers in the wrong spots, and they did their job and cleared out all the Kuiper belt objects.
Yeah, our solar system had a lot happen to it. Crap, I'm trying to look. I'm going to stop sharing so I can see the Q&A. There we go.
Okay, there you go.
Yeah, all right. So these are really good questions. Why didn't we see N2 sublimating? So there was a lot of sublimation of nitrogen ice. That's the heart of our models, is that the non-gravitational acceleration was due to just how much, and the mass loss and the erosion and the shape is due to how much nitrogen ice was coming off. We do see, spectrographically, we do see N2 ice, N2 molecules, more precisely N2 plus molecules emission show up. It's a very, it's kind of a difficult observation because it's very blue, almost the ultraviolet. It's like 3,800 angstroms. But it has been seen in other comets, including C 2016 R2. One of the differences is those comets are like many kilometers in size, with production rates, as in number of molecules leaving the surface, that are something like 1,000 times what would be predicted for Oumuamua. So I think no one really looked for N2, and certainly they didn't push the instrumentation down to the sensitivity levels that would have been necessary to see N2. So it could have been there and we missed it, is the answer to that question. My understanding is that Pluto has somewhat of a tail, or at least a noticeable atmosphere as it gets closer to the sun, as this object showed the material. So again, we don't really detect a tail. Pluto does have an atmosphere, though. There is an equilibrium between the amount of vapor that's coexisting with the ice, but it's gravitationally bound for the most part to Pluto. But some of it escapes. We don't see this part that escapes. But anyway, yeah, getting back to this, there probably was a lot of N2 that was escaping, but we would not have seen it unless you really were trying very hard to look at it. Right, another question, were they able to tell that it came from outside our solar system by the direction it was traveling? And it's really the speed at which it was going. So I should have mentioned this earlier, but it was traveling so fast when it was close to the sun that it couldn't be on a bound orbit. It was moving at 88 kilometers per second at its closest approach, which is way too fast to stay in orbit around the sun. So it's leaving our solar system, and it will make it outside our solar system and have excess speed to spare, 26 kilometers a second. And that means it also entered the solar system at 26 kilometers a second. So it just can't stay bound to our solar system. We know that from the speed.
So Steve, let me see if I can get Helen to see if she has a follow-up question or comment. So Helen, you're unmuted, so
Okay, I'm unmuted.
Yeah,
Can
so
you
if
hear me?
that answered your question, or if you have a follow-on question.
No, that answered my question. That was very clearly put. Thank you.
Okay, great. And
Great.
then
Yeah, thanks for asking it. I forgot to mention everything.
and then Joan, let's see. Joan, you're unmuted. Or if you unmute,
you hear
there
me?
you go. Yes.
Yeah, I was just curious about what the NEAS model says about how the orbits evolved to become so circular.
Yeah, thanks. And this is nice, actually. I'm glad Tom is unmuting people and I don't have to read them. So paradoxically, it's a strength of the model that the orbits are not so circular. When you think about how objects would have formed from the disk of gas and dust that surrounded the sun at its birth, you would predict that the orbits would be extremely circular, like the eccentricities of their orbits would be 0.001, whereas we do see that the eccentricities, the non-circularity of Jupiter's orbit, they're a few percent. So they're actually non-circular to agree that that is much bigger than you would have expected from their formation. And the NEAS model actually predicts how eccentric each of the planet's orbits should be. And the models show that each one has to fall in some sort of range, and they do. They fall in exactly that range. So that is actually one of the strengths of the model.
Is that good, Joan?
Oh yes, thank you.
Okay, great.
Great question.
Let me backtrack just one. David Baker, if you had a follow-on question or comment.
Fascinating, by the way. Thank you so much. Why is it that we cannot see the sublimation as this object goes around the sun?
Yeah, this is a really important, great question. And if it had been water, if it had been carbon monoxide, if it had been CO2, we were looking for those things. And based on the amount of emission you get from those molecules, we probably would have seen those species. N2 is just, it's a weaker emission, and it's at a weird wavelength, and 3,800 angstroms. It's a little hard to detect, but this was just a very small object. It was just a very small object, and not a lot of molecules were coming off of it. So it would have been a challenge to observe any molecule at all. Spitzer would have seen the water. It would have seen CO or CO2 if it had been there, but just barely. But N2, it couldn't have. And it wasn't looking. It wasn't designed to look for that. So you'd have to look from the blue near infrared ultraviolet, and you'd have to look from the ground, and our sensitivity is worse. It's a hard it's a hard molecule to see, and we weren't looking very hard. But it's really hope that if we see another of these objects, for example, the Vera Rubin Observatory is going to come online in the next year or so and scan the sky nightly, and let's hope that we see more objects like this. And I'm hoping that this sort of study motivates observations to look hard for that into.
Thank you. I appreciate it.
Thanks.
Okay, then we've got Walt. I think you can unmute yourself, Walt.
Well,
okay, maybe some people don't have microphones too.
Yeah, so I'm going
okay.
to
go ahead.
Yeah, so he asked, with all due respect, how have your theories been received by the astronomy community in general, or are there serious alternatives being discussed? So that's a great question. So for the most part, we'll tell you that the astronomical community is not too pleased to have the idea of a spaceship promoted so heavily, or solar sail, I should say, when first of all, it doesn't even make sense. There's internal logical inconsistencies, like it would have to be oriented from away from the sun, and yet we also see that it was tumbling. So you can't actually make it get a push away from the sun, which requires it to be oriented to the sun and also have that light curve. So there's a lot of things like that, but also it was just promoted so heavily by Abdulle to sell his book, and not really, you know, not very much time had elapsed to think about some of these alternatives, the things like we came up with. So in a sense, I would say that the majority of the community is kind of relieved that, you know, there's a pretty natural explanation and it seems to tick all the boxes. So I've gotten a lot of support from my co-author, and I've gotten a lot of support from the community. On the other hand, there are two people who don't seem too happy, and one of them is Abdulle, and he is attacking me in print in a lot of ways. And then also one group, Greg Laughlin from Yale, who's just convinced that it has to be hydrogen ice. Now, at least there, we're having a scientific debate, but I think that their idea of, I just don't think it's possible to make hydrogen ice. We don't see hydrogen ice. There's theoretical reasons why you couldn't. There's a lot of details with the model, but on the other hand, they don't like the efficiencies that we think you would need to eject material from. And, you know, these are things we can debate, and we are debating. And so it goes. But for the most part, I would say 80 or 90% of people who hear this think, yep, okay, that works. Thank you.
Thank you very much.
Okay. Yeah. And then Tom Curry doesn't have a microphone, so
yeah.
Go and
this object, when it came close to the sun, we calculated the temperature, which is really tricky because it's not like a black body temperature. That it's not like you put it next to the sun, you see how much energy is absorbed, how much is irradiated, balance it, calculate the temperature. That works for most of the objects in the solar system, but this thing was moving really fast. It was getting close to the sun really fast, and it was also losing so much nitrogen ice that the evaporative cooling is a major thing to consider as well. It's really interesting that if you go a few meters deep, it was as cold as it was in the interstellar medium. It was probably 25 Kelvin inside, but the surface was 47 Kelvin, even if it was closer to the sun than Mercury. So it was really hard to calculate that temperature, but it's yeah, I did show the graph that Tom is referring to, and hopefully that explains it. So it definitely didn't go as 1 over R squared, or actually in this case, black body temperatures tend to go as 1 over the square root of the distance from the sun, but it didn't follow that at all because it had all of these other things going on.
Okay, I think that cleared the question queue. I take it Avi's not going to have you write a foreword to any of his follow-up editions. if anything,
so
it brought, you know.
If we ever have an in-person meeting again and we go to a country buffet or something, I'll tell you all about it.
At least, you know, any kind of publicity is good, right?
One other question: how much did it slow down? And I'll just mention again. It was basically on a hyperbolic orbit around the sun, exactly as you'd expect from gravity. Started 26 kilometers a second, sped up to 88, slowed down to 26. What we're talking about is a variation on the 0.1% level of that speed.
Okay. All right. Thanks a lot, Steve. That was really informative, and not just about Oumuamua, but our solar system in general. Awesome.
Thank you very much. It was really my pleasure.
And back to you, Claude.
Okay. So I echo that, Steve. We really do appreciate it. Spending a lot of time sitting in my easy chair, watching YouTube videos. It was interesting to see a few recent videos that listed your data and you and Jackson and gave you credit. I'm sure you're not picking up the royalties from their YouTube channels, but I think it's significant research, and I think it's a great presentation. So I really do thank you for joining us tonight.
Thanks so much.
As we close up, a couple of things. Greco is open for public viewing, Saturdays only still. Weather for tomorrow night is again iffy, but we'll see. We did close last week. Maybe this week it'll luck out. And then if you are subscribers to the Astronomy magazine, January has an interesting article from Ted Forte from the Washuka Astronomy Club. They're kind of winter scavenger hunt. So there are a lot of interesting, fun objects, some of which I had looked at a long time ago and look forward to revisiting, and some others that were kind of new and fun. I just think it might be kind of interesting if you need a quick list of things to look for on a cold winter night. That would be a good choice. So if there's nothing else, I think we can close out with be safe and well. Our next meeting is going to be February 18th. It is a Zoom meeting, 7:30 p.m. Same time, same Zoom channel. And we wish you a good evening. Thanks again, Steve, and Hanaan for her presentation as well. We'll put some information about her presentation and the summer camp in the Observer, so be sure to check that for the next issue. And until then, if there's nothing else, see you next time. Good night.
All right. Good night, everyone.